Hey everybody, my name is Kelvin, and today I'm going to be explaining dynamic programming. Dynamic programming is a technique that is used in the programming world that is an optimization over just plain old recursion. Dynamic programming is often tested in technical interviews and is used in the day-to-day for optimizing time efficiency in your code. It's also a smart and powerful algorithm design technique. That means dynamic programming, while it may be difficult to grasp and understand at the beginning, is very important to know as a software engineer. In order to use dynamic programming, there are two criteria that must be satisfied before you can implement a dynamic solution. The first criteria is it must be an overlapping problem. This means that the problem can be broken down into multiple subproblems, which are reused several times, or it is a recursive algorithm that solves the same subproblem over and over, rather than always generating and solving new subproblems. The second criteria that it must fulfill is it must adhere to the principle of optimality. This was developed by Richard Bellman, and it means that the sub-solutions of an optimal solution of the problem are themselves optimal solutions for their subproblems. In order to demonstrate dynamic programming, we'll be writing a function that calculates the Fibonacci sequence given n. As a refresher for the Fibonacci sequence, it's a list of numbers where each new number equals the sum of the previous two. It starts at 0, 1, 1, 2, 3, 5, 8, 13, and so on. We start with 0 and 1, and then we keep adding the last two numbers to get the next one. We'll first start with a naive recursive solution. Suppose we want to find the value of Fibonacci given n recursively. To find this, we must compute Fibonacci n-1 plus Fibonacci n-2, following the logic that we discussed earlier. But the catch is, in order to find Fibonacci n-1, we have to calculate the values of Fibonacci n-2 and Fibonacci n-3. The same logic applies to Fibonacci n-2 and so on. Therefore, we clearly see that we rely on subproblems of the original problem to compute the solution satisfying the first criterion. We have our two base cases right here, and this is where we implement our naive recursive calls. We execute this code. Given n equals 30, the recursive solution executes in around 172 milliseconds. Now, how can we make this algorithm more efficient? Intuitively, we can see a possible solution. We can reduce the number of times the function is performed if we did not have to solve problems that have already been solved. In other words, we should remove redundant calculations. For example, in order to find Fibonacci 5 in a naive approach, we find the answer by recursively calling Fibonacci 4 and Fibonacci 3, which both then call subproblems of their own. Fibonacci 4 calls Fibonacci 3, Fibonacci 2 and Fibonacci 3 calls Fibonacci 2 and Fibonacci 1. As we can see, some of these functions are redundantly called multiple times. In a dynamic programming solution, we would seek to eliminate this redundancy. There are two approaches to implementing dynamic programming. The first approach is called tabulation, and it is also known as the bottom-up approach. The second approach is called memoization, and this is known as the top-down approach. Both have their own advantages and disadvantages, but they serve to accomplish the same goal. As you can see in the table, there are multiple trade-offs for the different methods. Ultimately, the choice of method that you decide to go with will be decided by you and your trade-off analysis. Tabulation, the bottom-up approach. As the name implies, the bottom-up approach to dynamic programming is an algorithm that starts from the bottom and accumulates answers to the top. This means that we fill up a table using results from subproblems, and then we use these results to find answers to larger subproblems until we eventually finish the problem. What does this look like? Here I've implemented the tabulation approach for the Fibonacci sequence. It has the same base cases, but where our recursive calls were, we create a table. In this function, we pass in n as a parameter to this function for the same reason we passed in n for the original function. Then we proceed with the function in the same way as a naive approach up until the else statement. At the else statement, our first step is to create a table to store our values. In this scenario, we initialize all the values in this table to 0 and set its length to n plus 1. we manually fill in the conditions for table at index 0 and table at index 1, or 0 and 1 respectively. We then use an iterative approach to fill in the rest of the list. Starting at index 2, we fill in the table with a Fibonacci sequence, calculating each value only once, up to the n that we would like. At the end, all that is needed is to retrieve the desired n from our table, and we have our result. The bottom-up approach to dynamic programming brings us from a bad, naive algorithm for solving the Fibonacci sequence, which was at exponential big O time efficiency, to one that is much better, at a big O time efficiency of only O of n. We can test the speed in a similar manner as we did the naive approach. As you can see, we've had a drastic drop in execution time, from 172 milliseconds to not even a millisecond. And we get the same result. Memoization, or the top-down approach. Memoization is referred to as the top-down approach because it starts from the original problem and then it works its way down, breaking the original problem into multiple subproblems and so on. It's much like recursion, but here, the results are stored somewhere, like a dictionary. Then, when we need the answer to a subproblem, we simply find the answer where we stored it and substitute it in. Suppose we have Fibonacci 1534 to calculate Fibonacci 1535, 1536. Suppose we need Fibonacci 1534 to calculate Fibonacci 1535 and Fibonacci 1536. Since Fibonacci 1534 has already been solved once for Fibonacci 1536, instead of redundantly solving it again for Fibonacci 1535, we can just get it from storage, therefore saving the computer the pain from having to calculate it again. This is our implementation of the top-down memoization approach to the Fibonacci problem. In this function, we pass in parameters n for the index n in the Fibonacci sequence and a memo. This memo is a dictionary. It will hold the results of our already computed results. The edge and the base case in this scenario remain the same. However, the only thing that changes in our implementation is the code in the else block. Our code checks if the nth result is in the memo dictionary already. If not, it does the computation and stores it in memo. If we've done the computation already, we simply just return memo at index n, which will give us the number that we want without having to do redundant operations. The top-down approach also brings us down from exponential O of n efficiency, to one that is also much better, at a big O time efficiency of O of n. Again, we've set up a timer to see how fast our Fibonacci memoization can run. If you take a look here, this is even faster than the bottom-up approach, at 0.062 milliseconds. Dynamic programming is a great tool to have in every software engineer's toolkit. We took a recursive idea, and we noticed the repeated subproblems, and then we chose a plan, whether to memoize to reuse answers, or tabulate to build them from the bottom up. The checklist you should keep is simple. First, define the state, write the recurrence, set base cases, choose an evaluation order, and pick memoization or tabulation. If you practice that flow on a few problems, whether that be Fibonacci or the coin change problem or the knapsack problem, you'll start seeing the same patterns everywhere. Thanks for watching, and I'll see you in the next video.